Welcome back, everyone. Let's just launch right into our with our next speaker, who is Gregory Deierlein, who is the John A. Bloom Professor in the School of Engineering at Stanford University. Go right ahead, Greg. Welcome.
Okay. Let me share my screen. Can you see the screen?
Yes.
Yeah. Okay, great. Well, thank you. It's really a pleasure to be here and to share with you some of the research I've been involved with, actually associated with two NSF centers. One is the Pacific Earthquake Engineering Research Center. This was a Generation 2 center whose kind of theme or mission was to advance performance-based earthquake engineering. I was deputy director for that center for a number of years. And most recently, I'm associated with the SIM Center, where we're developing computational simulation tools, both for earthquakes and other natural hazards. So I'm going to be focusing on some of the research we've been doing, kind of share with you on the earthquake engineering. In structural and civil engineering in general, we're faced with a task that we've always been building structures, oftentimes with incomplete knowledge, and earthquakes are a good example of that. These pictures on the left just show that in the US, for example, some previous earthquakes, 1933 Long Beach earthquake that did heavy damage to masonry buildings, many of those school buildings. The 1971 San Fernando that showed some vulnerabilities to reinforced concrete structures and other facilities, highways, and so forth. And then the 1994 Northridge earthquake. These are just a few. And my point here is that we're always, as engineers and scientists, we're always kind of learning from our experience and observations, combining that with theory and analysis. And nowadays that's computational, increasingly large-scale computational analyses, and then also experimentation. Now, engineers for a long time have when they see the ground shaking, they kind of associate it with, based on, say, Newton's second law, that we're going to have force equals mass times acceleration. Basically, that the earthquake shaking puts a lateral load on buildings. So for over 100 years, engineers have recognized that and built that into structures, but they didn't have information on necessarily how strong the earthquake shaking was, and also the tools to really design structures under that very large shaking. So I'd like to talk for a little bit about some of the work we do as engineers interfacing with earth scientists. These are geologists, seismologists, geophysicists. And in the history of kind of civilization, it's relatively recent we've understood earthquakes. This is an example of Professor Reid, his elastic rebound theory, which really established, the modern theory behind why earthquakes occur. This was really demonstrated dramatically in the 1906 earthquake, which was a rupture on the San Andreas Fault in California, and shown by this dramatic picture of the fence, kind of living proof of how the fault ruptured underneath and kind of offset that fence. Well, over the time since 1910, oops, I'm sorry, I went ahead one slide. We've learned a lot, and the science has advanced a lot, and earth scientists working at universities together with the U.S. Geological Service have mapped out faults. These are ones showing in the San Francisco Bay Area, Los Angeles. So the San Andreas Fault actually runs up the coast of California, but there are many other faults as the Pacific Plate pushes against the North American Plate, creating these fissures in the earth. So we've learned a lot about the earthquake faults. And again, these organizations led by the USGS create seismic hazard maps, which gives us a lot of information. It's based on kind of probability theory, kind of the risk of having high shaking. And you can see in this map here how in California and up the coast, very high shaking. But also, interestingly, we have earthquakes inside of plates in the North American Plate, for example, shown in New Madrid, Missouri, along the Mississippi River. In fact, some of the biggest earthquakes in 1811, 1812 occurred in that region. But the point is, now we have this information on what to expect in terms of the risk of strong ground shaking. So in the Peer Center, we developed what was called a performance-based engineering framework. And this kind of knits together all the pieces, starting out with interfacing with the earth science community to understand the intensity of ground shaking, what kind of accelerations can occur, and how do we mathematically describe those. then taking through our structural analyses, and there's been a lot of developments over the years on developing better finite element techniques to model the behavior of structures, to input the ground motion into structures, understand how structures deform laterally, but also then starting to translate that, how those deformations can cause damage to a building, to both the walls and the curtain walls and contents of the building. But then also relating that to the consequences being what's the risk to life safety, what might be the damage, how much does it cost to repair, the direct financial losses. And increasingly today, we're interested in resilience, which is how communities can bounce back from earthquakes. And that relates very much to the time it takes to recover or the downtime. So the performance-based framework as described here, which is a hallmark of the Peer Center, really knits together all these pieces. And you could think of it very multidisciplinary, starting with earth scientists, going through structural, geotechnical engineering, going into construction, but then at the very top, dealing with economists, sociologists, looking at the consequences of damage to buildings and how we could prevent that damage, but not fully prevent it in all cases for a lot of existing structures, for example. Now, what that framework's done is it allowed engineers to more confidently design remarkable structures. Shown here, this is an example of a building completed a few years ago in San Francisco. Very dramatic architecture that's shown here, but it uses a very innovative set of energy dissipating mega braces that you see there expressed in the facade of ductile steel fuses combined with oil dampers to dissipate energy. But it was the computational tools and knowledge about the ground motions and how structures respond that allowed engineers to design this, be confident about. This was an engineering firm, Arup, who did the design of this building using the performance-based methodology. Now, we don't just look at the large dramatic structures like that. In fact, the Northridge earthquake in 1994 demonstrated the vulnerability of many of the houses that we live in. And these are a couple of dramatic pictures here, and recognizing that that's a key thing in terms of the resilience of a community, keeping housing intact. So the question is, how can we address that both for new houses, but also the many houses that already exist that might have vulnerabilities? How can we address, make those houses stronger, more resistant to earthquake damage? So one of the projects we were involved with was to develop a technique called seismic base isolation, illustrated here in this house. And this is a technology that has been used on very large structures, the San Francisco International Airport, the new SoFi Stadium, the football stadium that's down in LA, and other structures have used seismic isolation, but it's a relatively expensive solution. But we wanted to look at ways to come up with a lower cost seismic isolation, and using, as shown on the left, what are called these sliding dish isolators. And these isolators, as shown in the middle graphic here, are inserted between the foundation of a house and the superstructure of a house. And what they do is when the ground shakes underneath the house, they provide an isolation plane and try to avoid the large accelerations going into the structure and then causing damage to the house. And shown on the right are a couple of graphics of the ground acceleration and the displacement that occurs on these isolators. Now, in this project, we did a lot of development of the materials of the isolators themselves, testing components of it, but we wanted to do a proof of concept on a large-scale test. And here we had the opportunity to do a test at the University of San Diego, University of California at San Diego, where they have the largest shake table in the US. This is an outdoor table, whereas you could see they could put very tall structures. These are earthquake simulators where basically using hydraulic pistons, they're able to reproduce earthquake ground shaking. And in this case, this plan dimension of 8 by 12 meters, that's what's shown in yellow, can move in 3 dimensions, 3/4 of a meter in different directions, representing earthquake effects. So we had the opportunity to build one of these isolated houses, and you could see in the upper left, if you look carefully, you'll see the shake table moving down below, and you see the building moving above it. But if you try to pay attention to the relative displacement between the ground and the structure, that's where the isolators are basically allowing relative deformations to occur. So rather than taking those deformations and forces into the house, these isolate it. And shown in the lower right of this is a video which is zoomed in looking at one of those isolators. It's basically a steel plate on the bottom on the foundation. It's a kind of a Teflon bearing pad, and you could see the relative sliding, quite dramatic shaking down below, and you could see how the relative deformation is taken up in these isolators. So this was an important test to be a proof of concept, to validate the design concepts and the analysis models that we were able to do, and really a joint effort, in this case, with researchers from Stanford and the University of California at San Diego. And you can see that quite dramatic shaking there. It's scary to watch in real time. Another, though, example of not looking at a technology, a high technology, the seismic isolation, but are there more cost-effective techniques to retrofit many older, vulnerable houses? This slide shows a dramatic image from that was taken after an earthquake that occurred in Napa, California in 2014. Coincidentally, the house on the right, these are both older houses, about 100 years old. The one on the right had a retrofit to its foundation. As you could see, it survived that earthquake intact, whereas the one on the left did not have that retrofit. It has a vulnerability below the first floor, kind of the crawl space between the first floor and the foundation of the building. And as you could see, that was a basic total loss. Major repairs would be required for the house on the left. So this is a case where the Peer Center worked together with the California Earthquake Authority. This is a group who kind of regulates insurance in California, but also tries to put together programs funded by the Federal Emergency Management Agency and others to provide funds and incentives for homeowners to retrofit their house to make the housing stock in California more seismically resilient. And this is, again, a retrofit of that foundation wall. So I won't go through all the details, but briefly, we could apply the performance-based methodology, so similar to what was applied to the tall building, but in this case, it's to look at a bunch of different archetypes, kind of prototypes of different configuration of houses, 1-story, 2-story, made of different materials, building computer models of them. And the point of this study was to try to demonstrate what's going to be the benefit of taking the effort and spending the money to do this retrofit of the foundation. And what's shown on the left side here, these are kind of loss curves that are used to assess that. On the horizontal axis shows the intensity of ground shaking. The vertical axis shows the damage or loss that would occur to the house. And the solid lines are showing what would happen, the damage to an unretrofitted house, and how by employing this foundation retrofit, which in this case is a relatively cost-effective, maybe $5,000 to $20,000 retrofit, depending on the size of the house, how you could dramatically, for a given level of ground shaking, reduce the amount of damage. And then with the CEA, California Earthquake Authority, kind of conveying this to homeowners in a way that they could better understand. This graphic on the right is showing, for example, that if a relatively large earthquake would occur, the types of damage in terms of dollars, repair costs, so $100,000 repair cost in some of these cases, or $200,000, $100,000, how by retrofitting the house, you can avoid those costs. So part of what we do in engineering is also, in this case here in civil engineering, is to interface with the general public so they can understand things. And in the case of private houses, kind of conveying the benefits of these seismic retrofit techniques. Now, more recently, we've gone from looking at individual buildings to looking at large regions of buildings. And this is made possible by using computational simulations to kind of scale up what we can learn from the laboratory and from analyzing an individual building. This is an example we're working with groups at the Lawrence Livermore National Lab who did a simulation of a magnitude 7 earthquake. This is a San Francisco Bay Area of the Hayward earthquake fault, which is a very vulnerable fault that runs right up through the East Bay, a magnitude 7 earthquake. And this is working in the Sim Center, getting an inventory of 1.84 million buildings in the Bay Area, making computer models of those, and then simulating how much damage and what would be the resulting loss. So the color coding here is showing relative the amount of loss that would occur. In other words, the damage and the repair cost that would occur in the area. But these high resolution simulations, they've given new opportunities to go beyond engineering an individual house to working with cities and other communities to try to engineer their cities. This is a zoomed in picture of the city of San Francisco, which is a mix of some very old buildings, some very brand new buildings like that 181, that tall 181 Fremont building I showed. But the question here is, how vulnerable is the city to large earthquakes, and what could they do about it? How does it affect different neighborhoods? Could be the Chinatown neighborhood, the downtown business district. And with these high resolution simulations, we could start to take our engineering models and start to interrogate that. So we did a study, for example, looking at the downtown San Francisco and asking the question, well, what's going to be the damage to buildings, but also if you have a damaged tall building, that might jeopardize not just itself, but also some of the surrounding buildings. There might be, after an earthquake, for example, a large safety cordon, a barricade that is put up if the other buildings are in the shadow of a damaged tall building. So this was a study where we looked at that implication of damage to tall buildings and how that could disproportionately affect a neighborhood and kind of impede the recovery. This curve, the plot in the lower center, is showing kind of the recovery of the neighborhood over time and how the impeding factor caused by this tall building cordon, the safety barricade, which is shown in orange, contributes to the downtime of not just the tall building, but buildings around it. And then the city of San Francisco, for example, with this knowledge, can then start to look at programs or policies that might want to address, say, requiring evaluation and perhaps retrofit of some older vulnerable buildings, ones that were built 30, 40, 50 years ago before we know the information we have now in modern tall buildings. So last couple of slides is we could then, as we look at our cities, not just take a snapshot of what the city looks like today, but to recognize that cities around the world, there's urbanization happening everywhere. Population is growing, and then populations are moving to cities. And just by virtue of there being more people and more buildings, there's going to be more risk in these cities. So the risk is going to continue to grow in the future. And this is where, as engineers, we could start to work with urban planners, sociologists, economists, and so forth, to kind of gauge what the risk in the future is and to see what steps we could take through better building codes, through retrofit policies, through land use rules, and so forth, to help minimize future risk, future generations. And so kind of just wrapping that up, all the technologies from performance-based engineering of an individual structure, going from ground motions to the effect of damage to one building, but then looking at collection of buildings, it's just an important contribution to, as engineers working with architects, urban planners, city planners, and others in the communities at large to help ensure more resilient futures. So I'd like to thank you for your attention.
Excellent presentation. Thank you very much, Greg. I think we have time for a question, and let me go ahead and ask that. So fabulous work, a lot of modeling and simulation engineering. But you highlighted throughout the presentation how important it is for engineers to be able to communicate and work with urban planners, with architects, and economists. Can you say something about how, what type of preparation an engineer should have to start understanding that integrative solution approach, and how, what you do really informs insurance, economic models, et cetera, and risk?
Yeah, well, I think one of it speaks to one, being curious. So even if you're an engineer and interested in a specific technical topic, for me, structural engineering, I've thought about that for now about 50 years. But I've always been curious about other things, and also enjoyed education courses in English literature, economics, architecture. So to appreciate these other disciplines and to learn enough about them such that you could be conversant and actually to take an interest in them. And it could occur through understanding history of cities by reading a novel. It could be, more like in the urban planning. And I think it's trying to communicate with people what we do as engineers, and to try to find commonalities with what other people are interested in. I think, and that's really what makes this fun. I mean, the technical part of drilling into our models is fun, but I think it's the human engagement and interacting with other folks on problem solving on a very large scale that's really fun and challenging.
Nicely stated. Thank you so much for that great presentation.